Hi boys and girls, this is lecture 2.3 in Unit 2, the topic Evaluating Limits Analytically. Limits can be evaluated graphically, numerically, and analytically. In the previous lecture, we discussed graphical and numerical methods, and in this lecture, we will focus on analytic methods for evaluating a limit. There are three such methods: direct substitution, dividing out, and a rationalization technique. Before we move forward, a word of advice: know your limits. First, we'll discuss direct substitution. Often, the limit is equal to the function value. Imagine that, boys and girls. When this is the case, use direct substitution to evaluate the limit. Here are functions whose limits may be evaluated by using direct substitution. The three basic types of algebraic functions: polynomial, rational, and radical. Direct substitution is valid for all points in the domains of these functions. Trigonometric functions. The limits of the six basic trigonometric functions can also be evaluated using direct substitution. Let's do a few examples. We're asked to find the limit as x approaches 2 of 4x squared plus 3. Now, since this is a polynomial function, we are able to use direct substitution to evaluate this limit. Since I know that the function value is equal to the limit, I'm going to evaluate the limit by directly substituting 2 into the function. This will give me 4 times 2 squared plus 3, which will be 4 times 4 plus 3. 16 plus 3 is 19. So the limit as x approaches 2 of 4x squared plus 3 is 19. Of course, that is also the function value, but for a polynomial function, the function value and the limit would be the same. Let's look at letter B. This is a rational function. Of course, we do need to be concerned about denominator issues, but remember, in this case, the domain of this particular rational function excludes only -1. Therefore, 1 is in the domain. Since it is, we can use direct substitution to evaluate the limit. Simply plug 1 in for all of the x values and evaluate the limit. This is going to be 1 squared plus 1 plus 2 over 1 plus 1. 4 over 2 is 2. Therefore, the value of this limit is 2. Remember, it's also the function value, but for rational functions, we find that the limit is equal to the function value for all real numbers that are in the domain of the function, which of course includes 1. Now, let's take the limit of this radical function. Often with radical functions, we do need to be concerned with the domain. However, that's only when the index of the radical is even. When the index of the radical is odd, the domain is all real numbers. Therefore, we will be able to directly substitute 3 into this function in order to obtain the limit. That's going to give us 2 times 3 squared minus 10. Of course, we're taking the cubed root of this quantity. 3 squared is 9 times 2 is 18. Minus 10 gives us the cubed root of 8, which of course is 2. And that is your limit. Finally, we'll take the limit of this trigonometric function. Since the domain of cosine is all real numbers, and of course the domain of the function x is all real numbers as well, we'll be able to directly substitute pi into this function in order to evaluate the limit. This is going to give us pi times cosine of pi. Since cosine of pi is -1, we end up with pi times -1, which gives us -pi. The limit and the function value at pi of this function. As we have seen, direct substitution, which is one of the methods of analytically evaluating a limit, is a simple matter of simply substituting the value into the function to attain a limit. However, if a limit cannot be evaluated using direct substitution, an algebraic technique may allow you to rewrite the function so that the limit may be evaluated. One of those techniques is called dividing out. A rational function can often be simplified using algebraic techniques to divide out a common factor. Here's our old friend x cubed minus 1 over x minus 1. Of course, 1 is excluded from the domain of this function, but we would like to find a limit at x equals 1, even though we cannot directly substitute 1 into this function to find that value. We have seen previously that a limit exists here. I wonder if there's a way to analytically determine what that limit is. Let's try some factoring. Since the numerator is difference of cubes, that numerator factors into x minus 1, x squared, plus x plus 1, of course, all over the original denominator x minus 1. Now notice that once we have factored this function, that denominator factor that was the sole reason we couldn't plug in 1 in the first place cancels out. So what we end up having is a reduced function that is identical to the original in every way except for that undefined point. Now we're looking for the limit as x approaches 1 of this function. Since we have used the dividing out technique, dividing out a factor, to reduce the fraction to a polynomial in which 1 can be directly substituted, let's do that. Let's just plug 1 in for x in both places. We find that the limit of this function as x approaches 1 is 3. Remember, that was the exact same result that we got when we were looking at graphical and numerical data surrounding this particular function. So that's an analytic method that can be used. Here's another rational function, and of course they're asking us to evaluate the limit at the one place where this function is undefined. Of course, x equals -3 has to be excluded from the domain because of this denominator. Well, what if this denominator wasn't here? If only we could somehow cancel it out. Well, let's try factoring the numerator. It turns out that this quadratic factors into x plus 3, x minus 2. How handy is that? Of course, x plus 3 is the factor that we need to get rid of so that we can plug in the number that we're evaluating the limit at. And so this is equivalent now to this reduced function x minus 2. Now it's in a form that we are able to use direct substitution for. We can put -3 in for x. -3 minus 2 is equal to -5. Thus, the limit of this function as x approaches -3 is -5. And that is how the dividing out technique works. Another algebraic technique for manipulating a function so that a limit may be evaluated involves rationalization. A function containing a radical can often be rewritten by rationalizing the numerator of the expression. The idea here with these two techniques, dividing out and the rationalization technique, is to rewrite a function in which direct substitution cannot be used. If we cannot directly substitute, we want to try to algebraically manipulate the function into a different looking function, a different form, one in which direct substitution can be used. And that's what these two techniques are used for. When you have a radical expression, you can use something that you learned back in probably Algebra 1 or Algebra 2 in order to rationalize the denominator of a fraction. In this case, however, we're going to rationalize the numerator. We're going to multiply the top and bottom of this function by the conjugate of this numerator. Remember, the conjugate is the same two terms but the opposite sign. In foiling this numerator times its conjugate, we're going to see some really wonderful things happen. So we're going to multiply the top by the square root of x plus 1 plus 1, and the bottom also by that same quantity, the square root of x plus 1 plus 1. Since we're multiplying a binomial times a binomial in the numerators, we will have to FOIL. The square root of x plus 1 times the square root of x plus 1 is x plus 1. The square root of x plus 1 times positive 1 is a positive square root of x plus 1. -1 times the square root of x plus 1 is negative square root of x plus 1. And of course, negative 1 times 1 is negative 1. In the denominator, we're not going to FOIL. We're going to leave x separate from this quantity because remember, we're hoping that x will cancel. So I'm just going to write this as x times the quantity square root of x plus 1 plus 1. We need x to cancel so that we can use direct substitution. Right now, x is the one thing preventing us from being able to plug 0 into this function. That's why I leave it unfoiled here. In the numerator, we notice that the radical expressions cancel, and of course negative 1 and positive 1 cancel, leaving just x over x times the quantity, the square root of x plus 1, plus 1. How fortuitous, because now we can cancel those x's, which leaves this simplified expression. We have 1 over the square root of x plus 1 plus 1. Now, let's try to evaluate the limit of this equivalent function. Remember, it's the same as the original, it's just in a different form. We algebraically manipulated it so that it looked different, but in this form, we will be able to use direct substitution. So I'm going to take the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. I am able to directly substitute 0 into the function now. I get 1 over 0 plus 1 is 1. The square root of 1, of course, is 1, plus 1, which is 1/2. And that's your limit. There are two special trigonometric limits, and they need to be memorized. The limit as x approaches 0 of sine x over x is 1. And the limit as x approaches 0 of 1 minus cosine x over x is 0. Now there are proofs in your textbook explaining how these limits have been derived utilizing the squeeze theorem. But at some point you need to make sure that you've memorized both of these special limits. You may wonder if you can use direct substitution here, but you can see in both cases you are unable to plug 0 in for x in these denominators. And since the numerators are not algebraic in nature, there's no way to reconfigure these algebraically so that the denominator will cancel. Thus, these limits have been proved and verified using the squeeze theorem, but you will not be able to use any sort of analytic technique to reconfigure the function. Bottom line, memorize these two special limits so that you can use them in problems like this one. We're asked to find the limit as x approaches 0 of tan x over x. Now, you might think that direct substitution will work, and you should always try that first. But right away, you see that you will not be able to plug 0 into this denominator. Let's see if we can use a trigonometric identity to rewrite this function so that we'll be able to use one of our special trigonometric limits. First of all, I'm going to rewrite this as tan x times 1 over x. Then I'm going to convert tangent to sine x over cosine x times 1 over x. And then if I want to put these two fractions back together, I can write this as sine x over, let's put x in front of cosine x cosine x, and notice that I have one of my special limits here. So I can rewrite this as sine x over x, one of my special limits, times 1 over cosine x. Now, we're going to take the limit of this function as x approaches 0. We already know that as x approaches 0, the limit of sine x over x is 1. So this part becomes 1 times 1 over cosine x. Well, I am able to plug 0 into this denominator. The cosine of 0 is 1. So this becomes 1 times 1 over 1, which of course is 1. And that is your limit. This leads to a general strategy for finding limits. First, learn to recognize which limits can be evaluated by direct substitution. You always want to try direct substitution first. Second, if direct substitution cannot be used, try to algebraically manipulate the function so that the limit can be evaluated by direct substitution. The two techniques you learned to do this were the dividing out technique and the rationalization technique. Further, it's possible that a trigonometric function can be manipulated so that you are able to use one of your two special trigonometric limits. Third, use a graph or table to reinforce your conclusion. To recap, limits are concerned with what a function is doing around a given point. Remember, we talked about the behavior of a function, and that behavior gives us information about the limit at a particular point. We noticed that limits can exist even when the function does not exist at that point, and you can find limits graphically, numerically, or analytically. It's important to develop an intuitive understanding of the limiting process of a function, to be able to calculate the limit using algebra, and to estimate the limit from graphs or tables. That's it for today, boys and girls. I leave you with a comparison of mathematics to other fields of science. God bless you, boys and girls.